I'd like to thank everyone for coming to another one of our Tides of Innovation Distinguished Speaker Series. Today, we're honored to have Dr. Witold Krajewski. He is the Rose and Joseph Summers Chair in Water Resources Engineering at the University of Iowa. He is also professor in the Department of Civil and Environmental Engineering and Research Engineer at IIHR Hydroscience Engineering. In 2009, he was appointed director of the Iowa Flood Center. He received his MS in '76, a PhD in 1980, degrees from the Warsaw University of Technology in Poland, in environmental engineering and water resource systems. He was a research hydrologist at the Office of Hydrology at the National Weather Service until 1987 when he joined the University of Iowa. His scientific interests concern measuring, modeling, and forecasting precipitation using radar and satellite remote sensing. His current research focuses on understanding the genesis and evolution of floods through field data and modeling, and the quantification of uncertainty in hydraulic prediction at the range of temporal and spatial scales. He's published over 270 papers in peer-reviewed journals on these topics. And with that, I'd like to welcome you, and you have the floor.
Yeah. Thank you very much. Thank you very much, Brian and Praveen, for the invitation. Like I said, I hope to visit in person, but today it was much more convenient to talk to you remotely. Let me start sharing the screen. And so can you see my opening water flow?
Yes.
Yes, okay, all right. So the topic is old. People have tried to forecast stream flow with hydrologic models for almost 60 years. And without those models, probably many more years earlier. So in that sense, there is nothing new. However, I hope to give you some new insights, perhaps, especially to challenges that we are facing as a community. But before I do this, I would like to formulate, the problem. So first of all, I see the problem as a problem of space-time nonlinear dynamics. So processes, happen on the landscape, water flows in the drainage, network. Rainfall has high level of variability in space and time. And then there are other players, involved. Well, now the forecasting problem is looking ahead. We would like to make a prediction everywhere and all the time. And everywhere means, something like this. So you can see that we forecast here flood potential at small streams and large, rivers, everywhere. That way, small communities that don't have even stream gauges, they can also benefit from our forecast. So this is something much more specific than what you hear on the radio when there is severe weather and they talk about potential for flash floods, but they talk at the county level, not at the stream or community level. So what are the ingredients of this problem? So we need to know what's going on. So we need to know the rainfall, which is the main, agent of stream flow here. So I will talk about rainfall-induced stream flow, leaving snowmelt and coastal processes away. We need to know the rainfall. So here I will refer to it as quantitative precipitation estimation and almost exclusively based on radar, weather radar, data. If we know what's going on from QPE, And we are, say, sitting somewhere, now, and we have interest everywhere in this domain. Well, then if we have a hydrologic, model, rainfall runoff model, then we are in a position to make this kind of a prediction. So now one can say, oh, okay, so we are looking into the future because the response is typically delayed with respect to rainfall, and we can say what's going, to happen maybe hours or days, ahead. So isn't that a forecasting problem? Well, so I say no. So for me here, the forecasting problem is if you also forecast the main input. So quantitative precipitation forecasting. So if, for example, you forecast that this storm will occur, then you are in a position to better predict the response. And here, without this prediction of the storm, it's clear that we would have underestimated, the peak in a serious, way. So that's my forecasting problem here that I'm going to talk about. So the key ingredients are QPE and QPF and a hydrologic model. Now, I will talk about the hydrologic model, but actually not a lot. Because you all heard about all sorts of hydrologic, models. So there is a plethora of them. But I will tell you a little bit about the model that we operate at the Iowa Flood Center. Well, because I like it very much. I think it's very elegant, and I think that it attempts to mimic how water flows in the natural environment. So, but this is not the only model that I will talk about. The other model that I will refer to is the National Water Center or National Water Model developed, operated by the National Weather Service. Unofficially. Well, our model has this structure. It partitions the landscape into only two elements, hill slopes and channel links. There is a one-to-one correspondence between a hill slope and a channel, link. The conversion of rainfall into runoff happens at the hill slope. Water is delivered to the channel link, and then the drainage network of streams and rivers aggregates, that flow. And the beauty of this is that the mathematical representation of this conceptualization can be written in the form of a system of ordinary differential equations, which are weakly, coupled, because the hill slopes don't talk to each other. They only talk to channel, links, and then there is a tree-like structure that moves water downstream. So if you divide based on digital elevation model data, for example, the state of Iowa, into hill slopes and the corresponding links, and then write the equations, fairly simple equations that conceptualize surface, unsaturated and saturated, zone, processes and the transfer between them. Then you have about 4 million equations. So it's a lot, but they can be, solved rather easily. So it's a nonlinear, system because the hydrologic routing here that we are using is a nonlinear equation. Well, okay, so I will not really say, too much about this model. We have been using it at the Iowa Flood Center for some 10 years now. Well, successfully in the sense that it gives, predictions as we speak. Performance, well, we documented in a number of journal, papers. So there are no surprises. We constantly improve, the model. Recently, we added a snowmelt component and also tile draining, component, to this, model. Well, but in the rest of the talk, in evaluation of different aspects of this forecasting, problem, I will use this Klein-Gupta efficiency. So I like it much more than the other popular Nash-Sutcliffe efficiency, just because it has these very nice, easy to interpret, components. We'll also talk about other measures of performance, peak, volume, time to peak, and so on. And then for categorical analysis, so this organization of these examples corresponds to contingency, table. And now I will say later on a little bit more about the threshold that distinguishes these categorical events. So those are the things that I will, talk about. And now the other component that is necessary here for streamflow forecasting. So radar-based QPE, or again, quantitative precipitation estimation. I will give you a couple of insights. I have spent many years studying the uncertainty of these, products and improving them. And still after some 30 plus years, I can say that we don't know everything that we would like to know about this problem. But we use the data, every day on our smartphones and such. So now let's say that we have a basin overlooked by, well, in this case, 3 radars. And now all these white points that you see are equal distance from the outlet. And now let's say that I make an overestimation error at one of these locations and an underestimation error at another location. Well, so I made a lot of errors, here, but the time you get to the outlet, well, they will cancel out, and you will not be able, to tell where I made those, errors, right? So the river network filters out these small scale mistakes, not only in the main input being the rainfall, but also in all other processes that are involved, like, for example, runoff generation. So, okay, so that's a good thing. But would be nice to also predict or estimate well the overall volume of water that is affecting, this basin, and not only this basin, but every other little sub-basin, here. So that's a task. So, well, another aspect that sometimes you hear about is the resolution. So radar data resolution. So of course we all think, well, the higher the better. And it's like, yes, I also agree with that. However, so here in this simply minded, simulation, study, so putting different radar data with different resolutions through a hydrologic model, like I was, showing you before. If we look at the peak flows at all scales, from a hill slope scale all the way to a large, scale, then this is what you get. So the reference here was like 1 kilometer radar input. So if you decrease this resolution to 2, 4, 16 kilometers, this is how your estimation of peak flows at these different scales, this is how it looks like. So clearly, like at the scales of higher than, say, 100 kilometers, it just doesn't matter if it's 2 kilometers or 4 kilometers. And to me, this explains why people like and use the so-called stage 4. So that's a domain, jargon, but some hydrologists they know what it is. It's a popular radar rainfall, product constructed automatically, but with some input from National Weather Service operators. So okay, so it's good to have good resolution, but it's not absolutely necessary. So it all depends on your scale of interest. Well, so this brings me to the following exercise that I wanted to share with you. So we will consider two radar-based products. One I refer to as MRMS. So this stands for multiple radars, multiple sensors. So this is a product that comes from the National Severe Storms Laboratory of NOAA in Norman, Oklahoma. And exists for the whole country. They produce it day in, day out. It is what you see here is accumulation over a few hours yesterday, as you can see from the calendar. This is hourly gauge corrected product. And on the right, you have an in-house developed product. So I will call it IFC or IFCA. Based on the same input, so data from the same radars, just a different algorithm of converting those observables into rainfall. And this product only exists over Iowa. For obvious reasons. Takes much more resources that we have to produce it for the whole country in real time, day after day. So you can see that they are similar, right? Maybe one could say very similar, but not identical, right? So okay, well, so that's enough for me to say. Now, which one is better? Actually, we published some studies where the conclusion was that they are about the same, in terms of accuracy comparing to rain gauges. So again, one is gauge corrected, the other is not gauge corrected, but uses different algorithm. So yeah, if we corrected it, what would happen? Well, I don't know, because the gauge network is sparse and not uniformly distributed over Iowa, so we just don't. So this is radar only product. Okay, let's go to the exercise. So now if you take the same model, exactly the same model, and you drive it by these two different products, and then measure the hydrologic results in terms of this KGE, or Klein-Gupta efficiency, at each stream gauge. These are USGS stream gauges, so roughly 140 here in the States. So if you add 90 and 50, so you kind of almost get there. So this is what you get. So in some places, one is much better than the other. In some places, one is very good, the other is very bad. So if you count the dots, so maybe you would say that MRMS is a little bit better. Okay, all right, fine. So now let's do the following. Let's make one equal to the other, but only in the mean. Okay, so we are not changing the distribution. We are what we call here, we equalize the mean. So the mean will be the same. There will be differences, here and there. This is what happens. So the output now from the same hydrologic, model, well, there are some differences in terms of KG, but not much. They essentially, these two products perform, the same, way with small differences. And the only thing that we changed was the mean. Well, so that's, and it doesn't matter if we equalize to one or the other. the very strong organization along this diagonal line would remain. So, but one can now say, okay, well, so if the mean is so important, maybe all we need is mean areal precipitation, like uniform, rainfall. Well, if you do that, well, then this is what happens. So it got worse, right? So we don't recommend this. There's another view of the same results. The map in the middle shows mostly small differences in rainfall after this equalization. On the left is the original with some significant differences, and on the right, significant differences up and down from the uniform, rainfall. So, okay, well, so this exercise brought us to think about, the mean, the total volume of rainfall. That is very important. Is seems like a dominating, factor, here. But this exercise did not help us to figure out what it should be. So we organized the following very simply minded exercise. So we said, okay, let's take these two products just for fairness and multiply them by different, factors. And for each factor, look at the response, hydrologic response, and see which factor leads to best, response according to different, criteria. So it's almost, high school exercise, but well, but we did it, and this is what we got. So I have lots of results, but I'm sharing only like the bottom line, here. So this is the distribution of different, statistics distribution over the basins here, and there's a simulation over like 7 years. And look what happens. So it's like if you find this optimal multiplier bias, but for each basin, well, then your different statistics behave, very, very nicely and much better than for the original, what I call here factor equal to 1, so which is just the original, data. Also, not a big difference between the two products, MRMS and IFC, which is not that surprising because they again, data come from the same, radars. Now, if you look at the map of that, so here is an example of an improvement. So for a couple of statistics, peak flow and the volume, and again, if you look at the colors, so we're talking about significant improvement, 50, 60, sometimes more, percent improvement over the original, value. So, but we also see in these maps that there are some patterns. And this is good because these are not just, it seems like these are not just like, random, factors that we found and now we don't know how to, what to do with them. So there are patterns that emerge, patterns that are associated with actually locations of the radars. And so that gives us, hope that we can, find some relationships, perhaps statistical, perhaps some other ones that will give us predictive power to do this in real time, because of course we cannot do this exercise in real time. So that's where we are. We also, of course, explore the seasonal effects here, and they are strong, as well. So that's one path for some small improvement to just change things seasonally. So, okay, well, so that's enough for today about the QPE. The bottom line from that is that there is significant potential in improving radar-based QPE to further improve stream flow forecasting. And I'll say, and stop blaming the models. All right, so let's move to the QPF. Well, so here we will focus our attention on this short-term 18-hour QPF. It is called HRRR for high resolution rapid refresh, right? So high resolution in space, about 3 kilometers, rapid refresh, hourly resolution in time, and so every hour day, the National Weather Service, they produce 18 hours of future, rainfall for the whole, country. So here is just, some math. So we did analysis for 7 years. So basically from the launch of this particular, product, every day, every hour, then you issue 18 hours of data, and then we look at it through the eyes of 8,000 USGS basins for the country. And we use MRMS as the reference. And those like Praveen who know me, they know that I would never call MRMS ground truth, so spend time fighting, this term. So, but I can call it a reference because no, there is no doubt that it's a better product than forecasting rainfall. And I will show you this in a moment. So this is kind of the framework, but to get you in the mood of, thinking about rainfall and the expected accuracy for QPF. So let's take a look at this example. So let's take a chunk of land, could be Iowa. Well, let's say that somebody forecasted this rainfall. And then let's just say that somehow we learned that this was the true rainfall. And now meteorologists, they would look at this and they would say, well, this was a very good, forecast, we got, the shape right, it's a little bit, stronger. We overestimated just a little bit. So yeah, it's a little bit off in space, but that is good. Okay, all right. So now hydrologists, view of this from the streamflow forecasting point of view. So, okay, if my interest is in this basin, here with the outlet at the red point, right? This is a terrible forecast, right? Because I probably triggered all sorts of false alarms. Now, if my interest is in this basin, well, I missed it, right? So again, it's a bad forecast. But if my interest is in this basin, this is actually a pretty good forecast, because whether the water moves on this branch here or on this branch, by the time it comes to the outlet, you cannot tell the difference. And if the quantity is roughly okay, then your prediction of stream flow at the outlet should be just fine. So that just shows us that this forecasting, skill is scale dependent. And now, how do we figure out how it depends as you go through scales from very small ones to very big ones? So, so I hope this got you in the mood. And now a little bit about the analysis of this massive, data set that the National Weather Service produced and we analyze. So they produced these QPFs to drive a hydrologic model, but for the hydrologic model, they only published, so to speak, the made available Streamflow, data for 18 hours, ahead. So it beats me why they limited themselves like this, but that's what they did. So that's okay. So we have this. So you can see here a division into east and west. And those are the roughly, I don't know, 8,000 gauges, didn't count, that we analyzed. This is where the national water model makes, prediction. Okay, so now clearly from my conceptual example, correct coverage is essential. If you don't cover your basin of interest with rainfall, then you have no chance. So here let's look at the conditional probability of again the forecast, given that the reference covers 90% of the basin, and we have a range of basins, here, and so we are looking what is the probability that HRRR covers 10, 20, 30, 40, and so on percent of the basins. But given that the reference covers 90%. Well, so what you can see is that actually for, and we are looking only 1 hour ahead, okay, next hour. So we can see that, yeah, this probability is actually, pretty high for, small values. And it remains high even for, large, values with more, scatter. The color scale here that you see, like bright blue, that's just the number of basins and hours that happens here, up to about 100 or so. So it's like more cases that are good. So, but now let's go 18 hours ahead. Okay, well, so we lost quite a bit, right? So still, we do have some basins where there is good, coverage. So again, references give me rain, and here is the response. But everything is much more, smeared, and that probability for many cases here is just not that high, 50%, 70%, or much less. So let's now take a look at at the quantitative, measure. So again, I'll take the simplest, doesn't need much understanding of some heavy-duty math, correlation coefficient. So how does that look like? So, okay, again, lead time 1 hour, just 1 hour ahead. Here we divided this domain into river forecast centers. So that's the organization of the National Weather Service. So again, the left panels in the west, right panels in the east, and this is how this correlation of total rainfall over a basin, hour by hour, how that looks like. And so again, the larger the basin, it looks, better. So with that correlation, 0.7, 0.8, sometimes, higher. Visible scatter in the west, we'll come back to that soon. But now, as we move through lead time, well, the whole thing goes down and down. And so for the basins that are in terms of USGS gauge representation, so most of them are between like 1,000 and 10,000 square kilometers, right? So thousands of square kilometers. So for those, we talk in 0.2, 0.3, 0.4, correlation, looking 18 hours ahead. You can call it 1 day ahead. So is this good? Is this bad? Well, I would say, that's bad because we were not doing, great in terms of coverage. And now we are not doing, great in terms of quantity. So we really shouldn't expect very good hydrologic, prediction here, streamflow prediction. But let's take a look. So, but before we do, I want to explain that scatter in the West. So, so one good question here about this forecasted rainfall would be, what about the climatology? Is it forecasting like rainfall, the rainfall that we know, and the differences in location and magnitude aside, or it's forecasting, something else, and so the simplest perhaps climatology would be probability of detection. So do we see rain the same way as our reference? Well, so here is the reference, and here you can see all sorts of artifacts from the radar, network. And by the way, this is based on the product, the MRMS. So this is not based on just the basic data as, radar is, scanning around. This is based on the product. This is the rainfall, product. And in the West, you can see all sorts of, blockages and gaps and this and that. We also know that there is less rainfall, like especially in Southwest. So clearly, I don't have basins here, the Western, basins here, but you can tell that claiming that the reference rainfall over those basins would be accurate, that's a stretch. So that explains, partially this scatter in the previous, statistics. But let's look at the same for the QPF. So this is how it looks. This is what, 1 hour ahead, 6, 12. Well, so clearly in the West, we have many mountains that block, the view of the radars, and we know from, visiting, there that it rains often. By the way, here the saturation of the red color happens at 15%. So 15% of hours of rainfall, this is what we get. But there was not a big difference between these different lead times. So in that sense, it's the same, rainfall that that the model, predicts, which is a good, thing. So yeah, I'll go back. Okay, so here we can see probably some data assimilation, radar data assimilation into the numerical weather prediction, model. That effect kind of, goes away as you go forward in time. Okay, so roughly, maybe this is correct rainfall, maybe not. So let's move, forward. So here we did the following exercise. That threshold that decides on what is an event, we set to mean annual, peak. So for each gauge, we calculated, that, and that roughly corresponds to bankful. So when it's above 1, so this is used for normalization, that quantity. So values higher than 1, then we call floods. and below water stays in the channel. So I realized this is very rough, but nevertheless, this is the exercise. And then we look at the detection of this. So this probability of detection, and this is at the gauge, each one of those that I was showing you. And this is, again, the median and the two quartiles here. And you can see, and everything as a function of lead time. And you can see that the performance goes down, very quickly with lead time. And this at the gauge where they already included the gauge value. And so this is just how they organize the data. I take no responsibility for that. However, because we couldn't decouple model output after data assimilation from without data assimilation, then we went one link of the river network upstream from the gauge and got the value. And that value, of course, has to be very, very similar to the value at the gauge without the data assimilation. And so this is what you will get. So we call it above the gauge. And so, so yes, it's worse, but you can think of this as the model on its own. Now, that's not even like exactly, true, because here still the model benefits from data assimilation if there is a gauge upstream. But still, the performance is like, nothing to write home about. So, well, and then my favorite here, persistence. So if you are going to forecast at the gauge, well, so can I by persistence. And I'm sorry to say, but I beat the model with and without data assimilation, so, but that we can come back to that. Now this is for basins that were on a small side, less than 1,000 square kilometers. So let's look at all the basins here again as a function of lead time. And so there's still this probability of detection. And now you can see as before that for the smallest, areas, the performance goes down very, very quickly, right? 6 hours and almost like no performance. And then for the next large area, again, goes down and down and down and down, and maybe after 10 hours, there's no performance. On the other hand, for the very large basins, there's no effect of that QPF because the response time is much longer than this, 18 hours. So you would have to wait a long time to see the effect of that. Now above the gauge, this is the situation. So again, the model by itself doesn't do as well. But the rest of the story is the same. So the performance goes, quickly down with lead time, but at the top, not much changes, here. So and these two are not, that different. So which again, it confirms that it's much easier to predict for large scales than for small scales, and that QPF affects much stronger small scales than the big scales, where there may be like no benefit of forecasting. Well, so let's take a look at this in a different way. So this will be now over Iowa. So that's why I have the Iowa here. We will be using our model that I talked about. The control run will be with MRMS. And then we will do like open loop simulation, like pretending that the input is the QPF. So we will make a run using the first hour lead time QPF all the way through 7 years, and then the second one, the second hour, and all the way to 18 hours. So we have like 18 runs of the same, model in a simulation mode. So we are not mimicking forecasting, here. And then the control run is with MRMS. And now this is what happens. So these are so KGE here on the lower right, and then the ingredients of the KGE, and clearly things are dominated by correlation. So correlation coefficient is much higher for MRMS than for any of these other QPFs. The interesting, thing, I have no explanation. So one would think that the further you go, that the worse it would get in time, right? With lead time. So the next hour should be better than the 18th hour, but it doesn't seem to behave, like this. So, well, it's 7 years of data. So I don't know. I have no explanation. So again, there could be something related to initial conditions and data assimilation, which has effect only on the next couple of hours, and after that it's the model on its own. So but anyway, so this is this one result. And now here we also did categorical analysis, but we had to change the threshold, and we had to change the threshold. We lowered it because this example is over Iowa, and we have been in a drought for the last well, 3 years, it looks like. So we didn't have many floods, and yeah, that's why I can retire now. So, but. So we lowered the threshold. So clearly we are looking at events, but many of them may just happen within, the channel and are not called, floods. But the analysis is the same. So and this what we got. So probability of detection, again, much higher for MRMS than from any of the QPFs. Well, false alarm, so much lower, although not that low. So I was surprised here. But probably the best, statistic here is the true skill statistic, which takes into account as a reference a random, forecast, and so you can say zero skill, here from 0 to 1, really. So, and okay, so what is interesting here is that these QPFs, they do have a non-zero skill, right? So these are predictions of rainfall and not, something completely different, from rainfall. But still, there is room for improvement here. No question. The same data, but in a map, view. So again, here just as an example, false alarm, rate. So you can see some strong colors here for these QPFs, and then a view as a function of scale. So here another puzzle. So short lead time, clear separation of these two. As you go further out, less separation. So I don't know what's going on here. So we have to think about it. So well, and then the final topic of data assimilation, I will not spend much, so I will use it as to wrap it up. So I will pose this basic question here, that like if QPF is so bad that you can miss your basin entirely, so you get a prediction with bad QPF. And then for data assimilation, you typically adjust something with the model, model states or model parameters or both. Well, you shouldn't be doing this because the QPF was wrong, and maybe there's nothing wrong with your model, and so there's just some food for thought to think about these standard setups for data assimilation. So we have to consider the effect of scales here and some other way that would quickly tell us if that QPF was good or bad. So this is one of these standard setups for data assimilation. Well, in time, but again, we have to be more clever about this. And also, I mentioned persistence. Well, persistence is data, right? No data, no persistence, forecasting. So here we have to recognize that there is a lot of information in the data. So again, this is persistence in time, but we can also do persistence in space, and there is some skill, there's no question. Again, better management of data with models can lead to further improvements, but still my attention here was on QPE that has high potential and QPF. I'll just skip this about spatial forecasting, and I will end by showing you this platform that we are developing. So again, these are all these gauges that the National Weather Service is making forecasts for. So they make forecasts everywhere for places without gauges, just to be fair. But where you have gauge, that's where you can evaluate what's happening. So we are building this platform for the rainfall and for the streamflow. And hopefully soon we'll release it, and anybody can very easily just see what's going on. It's a Google Maps based platform, and so with this I will stop. I want to thank you very much for joining me on Wednesday afternoon, and I'm all yours if you have any questions. Thank you.
For questions in the room, please raise your hand and I'll call on you. And I'll also be watching, we get the view straight, watching the gallery, pick people up online. Please just raise your hand. So first question in the room, David.
Yes, hi. It's actually nice to talk to you directly. It's a nice presentation. As I listen to this, and I come at this from a radar standpoint, since I understand that a little bit more. But you get into a lot of questions of what is truth, and and what are real values of precipitation. And correct me if I'm wrong, but it sounds like you were saying, based on a comparison of the model with the stream flow at a gauge, that you're estimating the amount of error that's in the radar estimates of precip. But you can flip that around too. Alan Hanlon, for example, looked at, assumed that the stream outflow was perfect, and he estimates that the precipitation gauges are incorrect by some amount dependent on wind speed. So how do you know which to assume is the correct base to determine this?
Well, so when I say error, I mean difference from the truth, but we don't know the truth. So I don't call it, error. Okay. So, and even if I call it bias, well, that's not error. It's just a component of the overall, uncertainty. So I don't know what's the truth. I'm saying that if you make adjustments to the current, products, then you can get better performance from the hydrologic models. So that's all I'm saying. So now it's like, can we figure out those simple manipulations of the current, products that we can improve streamflow forecasting by again, correcting. I can still call it a correction, because correction doesn't imply that I'm getting the truth. So that's all. So again, the conclusion here is that I believe that there is a potential for improvement in the current radar rainfall, products. Okay, to benefit streamflow forecasting. That's all.
Very good.
Next question. In the room?
There's, over the last few years, been more of a focus on urban flooding. And given what you've been showing here today, I'm just curious on your opinions. Do you think that with the current technology, with the quantitative precipitation forecast, QPFs, is there really any value in trying to forecast urban flooding at those small drainage scales? Or does there need to be some advances in the technology or the capabilities of forecasting to be able to accurately predict urban flooding, even at small lead times?
Yeah, so that's a good question. So clearly I was using here an example of this QPE that covers a continental, scale with high, resolution, but 3 by 3 kilometer resolution, that's clearly not adequate for urban flooding. So I think that there is still, potential in very short-term forecasting based on extrapolation of radar, data. So people have tried this just mostly by extrapolation and extrapolation of the movement of the radar, echo. And you have some skill, maybe 2-3 hours, ahead, no more, than that. And just a little, anecdote, here. So we all heard about AI, right? So and I said nothing about AI. So I'm going to say something now. So this seems to me like a perfect problem for AI. So because radar patterns, radar rainfall patterns are highly variable, very dynamic. Things appear, disappear, merge, and so on. So it's very difficult to just like even look at it and sometimes make sense of this and predict, what's going to happen in the next, 5 minutes, and so. Now in my college, I do have some experts in AI, and some of them, and they not in my department, in like electrical engineering, and they would come, to me like, hey, look, I got this, thing, and can you give me a problem, and I'll solve it for you. And so I gave them that problem, and then they never come back, so, and this happened, more than once, so so it's just not that easy, but I still believe that there is some, potential, there. And then, of course, if you bring some numerical weather prediction and do data assimilation correctly, I think we have a chance for this 2-3 hour lead time. So.
Are there any online questions? Please use that raise hand icon. Praveen?
Yeah, so Vitek, one of the question that comes to my mind is at the Iowa Flood Center, you have put significant investments in monitoring, developing new monitoring devices for Streamflow all across. I don't know how many you put in, but quite a few, right? So how does all that play in improving your forecasts here?
Yeah, so yeah, we have installed by now about 280 of those. So that's quite a number. So in our operational streamflow forecasting, we actually assimilate data from those. So we developed synthetic rating, curves for those stage-only sensors. The rating curves are developed based on open channel flow models, both 1D and 2D. So they are better than nothing, but they are not quite like USGS, which we call golden, standard. So, okay, now more about data assimilation. So nothing sophisticated like I was, calling for, here. So it really works as a correction downstream. And in data assimilation, the challenge, to me is how to make a correction upstream, right? Because downstream, well, that's kind of, easy. We can, see the effect and so on. So because of the large number of gauges that we have, both IFC sensors and then USGS, so, we keep our, forecasts, not too bad, so.
So in that case, are you able to somehow compensate for a bad precipitation forecast? I mean, the way you are showing, if you don't capture the area where it is raining, but your stream flow is showing a certain rise, you're going to say, okay, my rainfall was incorrect. I mean, that's the state variable that you adjust, not the soil moisture and everything else that goes into these assimilation models.
Yeah, so yeah, we don't touch those. We only stay with stream flow, and also we did a study of this asking this question: what is the worth of QPF for stream flow forecasting? And we did the study for Iowa only using our models because that way we had full control. So, for example, one of the runs, one of the scenarios was no more rainfall. So it's like, yeah, I know rainfall up to now, and whether it's raining or not, I'm assuming that there is no more rainfall. Just because, like, if QPF is so bad, then maybe it's better to just assume that there is no more rainfall and only look at that response to what already happened. And because we can repeat the forecast, let's just say every hour, then that helps a little bit. So anyway, the results of that study show that no, that's not a good strategy. That QPF, even the QPF that we have, this HRRR, does better with that than no more rainfall. So yeah, so I can now say, well, that's why our forecasts are not perfect.
So do you incorporate the soil moisture in these models or not? I couldn't
Well,
remember.
Yeah, no. So the model calculates soil moisture.
It calculates it, it's not taken as a measured value.
Yeah, no, yeah, it's just, it calculates it. So we did a study of assimilating SMAP soil moisture, data, and it was showing some slight improvement, perhaps. So again, yeah, we have a paper on that. but it's not a big effect. So we look at soil moisture, we have sensors around in the state, some 20, maybe with Iowa State, 40 stations that measure soil moisture at different depths. And we look at all this, but there is no automated assimilation.
David?
This is really a great topic. We know that, as you showed, that the radar probability of detection is, you know, highly varied with location. We also know it varies a great deal with the type of precipitation, such as widespread, fairly uniform rain versus local thunderstorm type of rains. But the probability of forecasting precipitation amount is also dependent on storm type. Do you think that the predictions could do better if you took into account the type of storm, that rather than trying to group all storms together, focusing on different specific types of storms?
Yes, so I was just showing you very partial results of a study that we are conducting actually with funding from Cairo. So you all know about Cairo, so Cooperative Institute for Research to Operations in Hydrology. So University of Illinois is a member of Cairo. So this is part of the study. So that's part of the plan, you know, to look into that. And so exactly how we are going, you know, to do this, I'm not sure at this, you know, point, but the geographic, you know, distribution and the seasonal distribution and then storm type distribution. So that's part of the plan. So.
Have you gone backwards and looked at like pulling out only the larger storms and see if they have better results than the smaller storms? I mean, like preliminary.
Well, it's
storms
uh,
scales?
Well, so those results are already partially included in what I was, you know, showing. So you would have to. So the results can be explained by the fact that large storms are easier, you know, to predict in some sense, you know, and so the location, of course, you know, so. But no, we have not, you know, split all these cases into fine analysis. There's just, you know, so much, you know, data and so much to calculate. So.
Are there any more online questions?
I have a question about your flood network, and I was wondering, you know, you have established a network of these gauges. Are you satisfied with the number of gauges you have and their distribution, or would you do them a little differently? Are there, would you start a little differently, or if you would just comment on how they're distributed across the state?
Yeah, so that's an interesting, you know, question. So that network was not established by some, you know, Uber design. It was the locations were based on opportunities when we started. Well, and actually we still do this. We ask the communities if they see a need. And if they do, and if we have the funding, then we go ahead and install those. And then there were maybe a couple of, clusters that where the funding came from some specific, projects. So it's like, for example, Iowa Department of Transportation. So they wanted to look at some specific bridges, and so they gave us, funding for some 20 or so of those. So it varies, but I would say that I like not necessarily the distribution, but I like the fact that this network responds to the local needs.
So I'm gonna ask my question again. If you could have it for your research forecasting purposes, would you distribute your stream gauges differently? Like if your goal were to start from zero,
Yeah.
just to keep the whole thing down, would you have distributed your gauges differently across the network?
Most likely. So then my thinking would be directed by the topological considerations of the river network in some large, basin where I could look at flow at streams of different orders. So another, consideration could be the width function, right? So the characteristics, a characteristic of again the topology of the river, network, and so yeah. So
Thank you.
Are there any more questions in the room? Any more questions online?
No more questions from me, but I just wanted to thank you, Vitek, for taking the time. It's very valuable, and I think this is very insightful. And I look forward to hosting you here when you have the time.
okay, no, thank you. Thank you, everybody. It was a pleasure for me to prepare this talk, thinking about all of you. So, and thank you, Praveen, and I promise to visit.
Oh, one last round of applause.
Thank you.
And thank you very much. And everyone else, we'll see you next week. Bye-bye. Thank you.